Welcome to Math317 Operations Research. Today we're going to be looking at the difference between continuous and integer optimization. So very briefly, this is probability stuff, I think. So you're welcome to take probability stuff. Okay. So what tools do we have available if something is continuous? Calculus, right? How many calculus classes have you taken? Okay, 3, 4, okay. Everybody here should have at least 3 calculus classes in the bank. This is one of the reasons why when we see continuous problems, we're happy. Discontinuous problems, discrete problems is a little bit harder. So let's do the sum problem. And to do this properly requires us to use almost everything we've done from Calc 1 to. So let's assume we have some number s, which is a sum. Maybe s is equal to 100. But you can do it more generally. And I want to write s as a1 plus a2 plus plus an. And I want each ak to be greater than or equal to 0. And I want to maximize the product of the a's. Okay, so whenever you see a problem, the first thing you always ask is, what conditions are we putting on and why? Why am I assuming the a's are greater than or equal to 0?
You have a negative.
So what could I do? Well, so if I have a negative product, it just won't be one of the maximum values.
You can make 2 of them negative and then make one other one arbitrary.
Yes, I could do negative 100, negative 100, 400, and then negative 100, negative 100, 200, and then would carefully balance out. And so I could make the product arbitrarily large if I allowed negative values. So I clearly don't want to allow negative values. Do I want to have ak greater than or equal to 0, or could I refine that a little bit? Yeah, there's no reason why I would ever choose any of the AKs to be less than 1, unless my number s is less than 1. So let's assume all the a's. Okay. Now, what makes this problem hard is we don't know how many things to split it into. Does anybody have any thoughts as to what might be the best?
So, basically, I'm pretty sure it's that you want to have every a should be either 2 or 3.
Okay.
Because basically 2 times 3 is 6.
Yes.
Whereas 2 plus 3 is 5.
You're very close.
Sorry. So it's what was it? I don't remember what it exactly was. Oh, sorry.
It's 2 times 2 times
2
2
is 8
versus 3 times 3.
Versus 3 times 3, yes.
So would we want a number like 10 as one of our terms? What could we replace 10 with?
For example,
5 and 5. Or I want to do something easier. Replace it with a plus 2.
Just a clarification, is n fixed for the problem?
No.
Are we giving
N is free. N is free. And that's what makes the problem challenging, is you don't know what n is. So if I had a number like 10 as one of the summons, I would replace the summand of 10 with 8 plus 2. What if I had 9? I would replace it with 8 plus 2. Yada, yada, yada. 5, I would replace it with 3 plus 2. And what about 4? Would I replace 4 with 2 plus 2?
Can you clarify the 9?
Yes.
8 plus 1.
No, I don't want to do 8 plus 1.
7
7
plus 2.
plus 2. Should I replace the 4 with 2 plus 2?
You can.
It doesn't matter. So this is a chance to talk about things we've seen before. Remember when we had linear programming and we had, for instance, maybe the objective function was parallel to one of the constraints, so we had a bunch of solutions. Just choose one of the vertices just so that you have a definitive procedure that returns you to a certain place. I would much rather have 4 out of play and not have 4 under consideration. So I will absolutely replace 4 with 2 plus 2. So you only have AK in 2 or 3. And so now it just comes down to, do you want more 2s or do you want more 3s? And then as was remarked, 2 plus 2 plus 2 equals 3 plus 3. So in terms of the contribution to the sum, 2 3s gives you the same contribution as 2 2s. But the product is 8, which is less than 9. So what this is telling you is whenever you have 3 2s, you always replace it with 2 3s. And then you're stuck with, you might have a little bit of a leftover. You might have a 1 left over. Well, if you have a 1 left over, just put it in with a 3. So this finishes the problem in the discrete, in the continuous case. We can ask, what would be the best solution in the continuous case, where we no longer have to break it into integers? So here, this is all integers. Now, we are choosing 3 over 2. So I'm going to draw a little bit of the real number line for you. Here's 0, here's 2, here's 3. Are there any numbers you might want to add that might play a role in this problem? E. Where is E? Here's 2.5. Is E closer to 2 or to 3? Yeah. That's going to play a key role in the solution of the general problem, is that E is closer to 3 than it is to 2. If you've done anything in computer science loves to work base 2. For disk storage, and this is actually related to disk storage, base 3 is a little bit more efficient for disk storage than it is for base 2. But in terms of a lot of the algorithms love base 2. All right, let's consider the continuous version. So a lot of the argument goes as before. So we can replace 4 with 2 plus 2. But then at that point, we're stuck. And so now, all we know is we have all the numbers, and now they have to be not just in the interval 2, 3, but let's say in the interval 1, 4. And it might be nice to have a closed interval if we want to use tools like calculus. All right, so we want to do this optimization problem. The problem is we don't know what n is. So what should we do?
Maybe fix the value of n.
Yeah.
So we get as a function of n.
Fix n, get maximum, then we vary n. So for each fixed n, we're going to get a maximum. All right. What's the easiest choice of n?
1.
1. All right. If n equals 1, then you just get a1 is s. Not a big deal. You've actually done the n equals 2 case. So you want s to be a1 plus a2, and you want to maximize the product. You've done this in calculus.
Square root of s.
It's the square root of s. Does anybody know what type of problem they often call this? Sometimes it's called the Farmer-Brown problem.
Oh, is that the one with like the square? And
Yes,
like,
Farmer Brown loves rectangles and will not consider a shape other than a rectangle for his cows to graze. And so Farmer Brown has a certain amount of fencing. And what is the maximum area Farmer Brown can enclose? Anybody ever read the story Click Clack Moo? For cultural extra credit, what is the first line?
Click clack moo cast the type.
That's the title of the book. What's the first?
What's the first line? I don't remember. It's been too long.
I think the first line is Farmer Brown has a problem. All right. So if you have something like this, here's A1, here's A2. Or technically, this would be maybe half of A1, half of A2, right? And everything says S is like the semi-perimeter rather than the perimeter. Doesn't really matter. As an aside, do you know about Farmer Brown's brother, Farmer Bob? So what does Farmer Bob have?
So coastline across.
He has a coastline. So Farmer Brown is on the coast. And the question is, what shape does Farmer Bob take, given that Farmer Bob is on the coast? You can set up the problem exactly as before and do calculus, right? You can say, here's y, here's x. We want, x plus 2y equals s. We want to maximize x times y, which is the same as maximizing x times s. Oh, actually, it's better to replace x rather than y. So x is just s minus 2y times y. And that's not a hard thing to maximize. So we could solve the Farmer Bob problem using calculus. There is a one-line elegant solution using symmetry. And it uses a superhero from the Marvel universe. We've got a coastline.
Are we Thanos snapping half of the rectangle away?
I'm sorry?
Are we Thanos snapping half of the
No,
rectangle?
no. Although that actually would go well, and then 5 years later we'll get the solution. What superhero would be in the water? Aquaman.
That's DC. Oh.
So imagine at the same time Farmer Bob is trying to maximize his pen for his cows, Aquaman is trying to maximize his pen for his fish. And then if you put it together, it's the same perimeter as, and then you know the square is the best solution in that case, so each one has to be half the square. So I really like the second solution of using symmetry, reducing it to a previously solved problem. All right, we could continue to go like this. We could now try to do n equals 3, etc., etc. What do you think is true for given n? What's your conjecture? Yeah, equal split. Your A1 equals A2 equals AN equals S over N. That the best you can do is when they're all maximized. Real analysis is sadly not a prerequisite for this class. How many people have taken real analysis? Okay. How many people will someday take real analysis? Okay. So what I'm going to do is I'm going to give a little bit of a pitch as to why you might care about a class like real analysis. What we would love to do is to say that a problem like this has a well-defined solution, that there is a choice of A1 through AN that maximizes things. And if there is, then we'll find it. But you don't necessarily know that there is a maximum. So for instance, if I give you the function f of x equals 1 over if I do the function 1 over x, this blows up as I go to 0, like this. And so if I looked at this on the interval 0, 1, this function has no maximum. So not every function is going to have a maximum. The big result in real analysis is if you have a continuous function on a closed compact set, it has a maximum value. And so this problem will have a maximum value. All the a's are clearly between 0 and s. And so we have a closed set. It has to obtain its maximum value. And so there's a beautiful proof that the maximum value is when they're all equal. So real analysis implies there exists a maximum. Assume not all equal. Okay? So without loss of generality, which two are not equal? Right. So assume A1 does not equal A2 without loss of generality. What should I replace A1 and A2 with? The average. Replace it with A1 plus A2 over 2, A1 plus A2 over 2. We're just using the n equals 2 case. We know in the n equals 2 case, if you have a fixed sum, the largest is when they split equally. So if we have a place where they're not all equal, well, we'll place the two of the ones that aren't equal with their average and then increases things. Because a maximum exists, we can assume we were at the maximum point. And if they weren't all equal, by replacing, we now have something that's larger, contradiction, they were all equal. We needed to know that the maximum existed. Otherwise, you could have this terrible endless cycle of constantly replacing things. And then you might ask, well, maybe that's not so bad if I have an endless cycle. Maybe I can prove that it converges. And if I just keep iterating the process, it will converge to something. We don't have to prove that, but if you want to, that's something you could try to do. So we now have the maximum value. So the conjecture can now become a lemma. I don't think it's quite good enough to know the theorem, but they're all equal. So now we want to maximize with respect to n. So what we can do for fixed n, the maximum product is going to be, let's call it f of n, and it's s divided by n to the nth power. And now we're getting to the point that's going to really lead into operations research. We want to maximize this function, and unfortunately, this is a function defined on the integers. Calculus is not applicable. So we have to vary n discretely and see what's the best. Oh God, that's painful. Can anybody give me something else that we could look at that's closely related to this?
The same function but defined on the real numbers?
Yeah, just replace n with an x. Could you allow n to be a real number?
I mean, if it is.
No. I want a yes or a no. Can you allow n to be a real number? Yes or no?
Yes.
Yes. Can you change the order of your axes in economics as to which is quantity and which is price? Yes. Should you do that? No. Right? When you look at it, it's nice to be able to look at things and know n is an integer. And so I would not be comfortable having n as a real value. So let's use something else. Now we have a real valued function, and we can try to optimize this. All right? And this is going to be e to the x log s over x, which is e to the x log s minus x log x. So some of these, functions, these cookbook functions that occur in a calculus homework assignment, we're actually now finally using something like that, where we actually have x to the x. All right, when we take the derivative, well, what rule do we use to take the derivative of this? Chain rule. What's nice about this is you're going to just get this back and then the derivative of the exponent. So I just get back my original function, f of x, and I know f of x is never 0. And now I have the derivative of this. So the derivative of this, I take the derivative of x log s, that's just the log of s. And now I take the derivative of x log x, I use the product rule. When I take the derivative of x, I get log x. And when I take the derivative of log x, I get 1 over x. X times 1 over x is 1, so I get minus 1. So if I want f prime of x to be 0, then I want the log of s divided by xe to equal 0. Just using my log laws. 1 is the same as the log of e. Is this how I find where a function takes on its largest and smallest values? Crap. All right, tell me where I'm traveling at my fastest speed, okay? I should have been holding the clicker with that. Where was the fastest speed? The wall. Was the derivative 0? No. What else do you need to do? Check endpoints. Right? Always, always, always remember to check endpoints. If I take s, if I go for the extremes, what would be the extremes? Well, it would probably be basically n equals 1, and that's going to be a very small product. And then if I take n to be getting very, very, very large, the product is going to be less than 1. So you can see that the endpoints are not going to be the winners. When is the log of s divided by xe equal to 0? When the inside is 1. So we get s divided by xe equals 1, which implies x is equal to s divided by e. And now the pieces are s divided by x, which is just e. So you want to break it up into pieces of size e. And the number of pieces you want is s over e. Now, unfortunately, it is unlikely that s is going to be a multiple of e, and that you're going to be able to do this. So the question is, this is the real optimal. How close is the discrete optimal to the real optimal? In this problem, we're going to be able to prove how close it is. In the next problem, we're going to show they're going to be very far apart. So this is a chance to introduce you or to familiarize you with some results that were done in calculus classes when I was young. How many of you have done curve sketching? By using derivatives and second derivatives and stuff like that. So they used to have us plot the signs of the first derivative and the second derivative and use this to sketch curves with concavity and all that stuff. We're not going to go to that level. But here's my x-axis. The key points for us maybe will be we'll do 1, we'll do an s over e. And then down below, I'm going to write the values of the first derivative. 1. When we choose x to be s over e, the first derivative vanishes. If x is less than s over e, is this quantity going to be greater than 1 or less than 1? I can rewrite it if you want as s over e divided by x. So when x is greater than s over e, is this greater than 1 or less than 1? Less. What's the log of a number less than 1? Negative. So I know the first derivative is negative from here onward. The function is decreasing. What if x is less than s over e? What is true about this ratio? It's now greater than 1. Its derivative is positive. Oh, life is good. Right? When you look at this, the function is increasing until it gets to s over e, and then it's decreasing. So the curve looks something like that. So what is the best integer optimal? Well, all you have to do is just check the integers immediately before and after s over e. And one of those two will work. Because we are in the fortunate situation where the function just goes up and then just goes down. In the general case, we are not going to be this lucky. So I really like this as a calculus problem. It uses a lot of the different techniques, good differentiation results, functions, x to the x, actually arising in a problem. It has applications. This has applications to storage, and why base 3 is sometimes better than base 2. All right. So now let's move on and do a different discrete problem. How many of you have seen the knapsack problem? Okay. It's actually interesting now as to how much, how many times people actually bring books and whatnot with them because so much is now available online. So we are going to assume that you have a knapsack, and this knapsack can hold 150 kilograms. Nope, 100 kilograms. Holds 100 kilograms. And you have 3 possible items that you can put in. And you can fill up your knapsack as much as you want with any of these. It's like Halloween. And the first, so item value and weight. So item 1 weighs 50 kilograms. Oh, sorry. And its value, oh no, the first weighs 51 kilograms. Sorry. And it's worth $150 per unit. The second item weighs 50 kilograms. And it is only worth $100 per unit. And the third one also weighs 50 kilograms and is worth $99 per unit. All right, so I see at least one person snickering. Which is the odd one out? Right. Is there any reason why you would want to buy 3? The only way, I'm sorry?
You're out of 2.
So they're out of 2. Or perhaps it's more than just how much the knapsack can hold. There's also the volume. It's more than just the weight. And maybe how the objects are shaped matters. But unless you have something strange like that, clearly 3 is right out. Right? Because 2 is better. It's the same weight, but more. Which would you rather have? Item 1 or item 2? Item 1 is definitely giving you more dollars per unit. If you could do the continuous, it's all item 1. What if you can't break things up? Any Seinfeld fans here? All right, Seinfeld cultural trivia. There is an episode involving Jerry and Kramer, where Kramer wants to just take part of something and pay for just part of it. So I'll let you see if anybody can remember this one.
I think you've mentioned, is it a hot dog or a hot dog bun?
It's not a hot dog bun. That's Father of the Bride. So in this episode, Kramer and Jerry are talking, and Jerry makes a remark about how Kramer's always coming into his apartment to take his food. And Kramer says, well, you can come into my apartment and take my food. Well, you don't have anything I want. I'll start paying you for the food. We'll make a little list, and at the end of the week, we'll square up. And so he sees the list, and one bite out of an apple, one sip from a can of soda. He goes, no. You know the sound that you hear when you open a can of soda? That's you buying the entire can. You're not buying a sip from the can. So over here, you probably can't just buy part of a unit. So if we do things discretely, what are your choices if you could have 100 kilograms? Yes?
So you can only have one of item 1.
So you could have one item 1, and that will give you $150. Or what could you do here? 2 item 2, and that will give you $200. Now, not surprisingly, these numbers were deliberately rigged. But this is what you have to be afraid of when you are designing your systems. What is the worst possible case? What could happen? In this situation, the discrete optimal is nowhere near the continuous optimal. And that's something that we have to be very, very careful about. Okay. Any questions about this? So for a lot of things in the real world, we are stuck with having to do integer amounts. You cannot do half of a flight, and you have the plane fly part way and then change. Unless, can anybody give me a situation? I can think of a few situations where a plane would change. Emergency landing. So can you give me situations where you might have emergency landings?
Someone has like a heart attack on the
Someone has a heart attack and they're in first class, and so if it's coach, oh, I'm sorry, you're group 9. So heart attack for something, for medical emergency, the planes will land. There's another one. In fact, yes.
I mean, it's happened with fueling glitches, like when they completely run out.
When they completely run out of fuel. So sometimes the weather is worse than they thought, or sometimes they can't get into an airport and they're circling around for a while and they run out. My favorite is where the plane then returns to where it started. I'm sorry? Yes. No, the number of bad flights I've had is, I could go on for a long time. I actually once had a direct flight, I guess, from one Washington airport back to itself. And then there is another one that affected the entire nation. Thankfully, it's only happened once. 9/11. And I think after the second plane hit, all the planes were told to immediately land as soon as you could.
A good amount of them went to Newfoundland.
I'm sorry?
A good amount of them went to Newfoundland.
Oh, really?
Canada. Yeah.
Oh my.
There was a musical about it called Come From Away. It's a very good musical.
Interesting.
It's off the summer.
Interesting.
I just stayed there for 5 days because that's how long it took.
Right. And I was coming back from my honeymoon and we came back 2 days before September 11th. And so we almost had a significantly longer honeymoon. But for a lot of travelers, they were stuck for several days. And then you have concerns about, can the airports, handle? Because not every airport can handle every flight. So when we're trying to solve things, it is essential that we have techniques that can solve these integer valued problems. Right now the college is considering hiring new professors. You can't really hire a third of a person. Unless maybe you talk to some other schools. And the 5 colleges in the Amherst area, they actually are able to do something like this, where we'll take half of the position, you take a quarter, you take a quarter. And you can break something up like that. So you might be able to refine things more than you initially thought, but for a lot of these problems, at some fundamental level, there is a discreteness that we need to deal with. I want to talk a little bit about some of the possible research projects. So I'm going to talk about a theoretical research project. There's a great old theorem. So consider the numbers 1, 2, 2n. So the claim in any set of n numbers at least 2 x and y have x divides y. That it is not possible to choose n plus 1 numbers without having one divide another. What's an easy number to put in your set to make sure that this is going to happen? 1, right? If you put 1 in your set, then you're done. So before we prove this, there was a typo initially and I wrote n. What would have happened? Is it possible to choose n numbers and have none divide each other? That have no pair where one divides another?
Choose the top half.
Excellent. So if you take n plus 1, n plus 2, 2n, no pair works. So it's always nice to have a quick result that we do need to have at least n plus 1. So the proof is really elegant. Has anybody seen the proof of this?
So first we kind of factor each number into its even and odd.
Good. And what's the main idea you're going to use for the proof?
Pigeonhole.
The pigeonhole principle. How many people have not heard of the pigeonhole principle? Everybody else has heard of the pigeonhole principle? So the pigeonhole principle is one of the most important, powerful techniques in mathematics. And there's a lot of ways to phrase it. So one way is imagine you have n boxes. I'm not sure if I'm allowed to do this anymore. And you have a person with a pigeon gun that shoots pigeons. Okay. No pigeon is harmed. They find this very fun and relaxing and soothing. Right? And the pigeons are shot into the different boxes. And you shoot m plus 1 pigeons. If you shoot m plus 1 pigeons into m boxes, what can you tell me?
One box. There's at least one box with 2 pigeons.
At least one box has 2 pigeons. Because if each box had at most one pigeon, and there's only m boxes, that only accounts for m pigeons. So at least one box gets 2 pigeons. It's amazing how many problems can be solved using this. It's a wonderful, wonderful technique. And so the idea for this problem is write any number k as 2l plus, let's do it this way, 2a plus 1 times 2 to the b. So we're going to write any number as an odd number times the power of 2. Okay? So whenever you're doing a pigeonhole problem, you always have to decide what are your pigeons and what are your boxes. All right? So we can write every number as an odd number times the power of 2. What are our boxes going to be?
Odd numbers 1 through 2.
Odd numbers. 1, 3, 5, 2n minus 1. How many boxes are these? N boxes. And what are our pigeons going to be? So we're choosing n plus 1 numbers. So those numbers are going to be our pigeons. So at least one box gets 2 numbers. Maybe it's box 5. And if that box gets 2 numbers, then one of the numbers is going to be of the form 5 times 2 to the b1 and 5 times 2 to the b2. Because they have the same odd part, the one with the smaller exponent divides the larger. And so you have to have one number dividing another. So the hardest part about the pigeonhole problems is figuring out what are your boxes and what are your pigeons. You know, the idea here that you want to write your number as odd times power of 2, that's really clever. Okay, why am I asking this problem? Well, we just had a distinguished visitor, Hugh Montgomery. He is probably the author of one of the first 5 research papers I read when I was a student starting to do research. Huge in terms of connections between number theory and nuclear physics and mathematical physics. And he was talking about when he was young, he met the great Erdős. Is there anybody here who does not know what an Erdős number is? Okay, do you know what a Bacon number is? So a Bacon number is, have you been in a movie with somebody who's been in a movie with someone who's been in a movie with Kevin Bacon? And there's a great website, The Oracle of Bacon, and you could put in obscure French actors from the early 1900s, and almost surely their Bacon number will be less than 6. It's incredible how well connected things are. Well, above the Bacon number is the Erdős number. Have you written a paper with Paul Erdős? Or have you written a paper with somebody who's written a paper with Paul Erdős? And so on and so on and so on. So my Erdős number is 2. A few years ago, I wrote a paper with some of my probability students in Cameron and Kayla. So they have an Erdős number of 3. And they sometimes put on ears, oh, your Erdős number is... The Erdős Bacon number is, do you have a finite sum of your Erdős and Bacon numbers? So I'm blanking on her. She was in Wonder Years, Danica, is it Geller? She went to, I think, Stanford for psychology. She's got a very low Erdős Bacon number. I think Natalie Portman also has a very low combined Erdős Bacon number. You know, you need smart people who have gone on to acting. I wouldn't be surprised with all the things he's been on that he would have something. So Erdős gave him this problem and asked him, okay, so if you look at a set of n plus 1 numbers so that there's no way to do this without having one pair divide another, without having one element of a pair divide the other. What if I now consider, just take n numbers, from 1 to 2n, such that you never have x divided y. Is it possible to do this? Yes, in fact, we got an explicit construction earlier. Just take the last n. let f of n be the smallest element in any set that works. So what I'm saying is, consider all possible sets where you do not have any number dividing any other. And for each set, look at the smallest element, and then take the smallest of all the smallest. And there is an answer for what Fn is. But I don't think anybody has looked at the second smallest. And you can do the second smallest two different ways. You could say, I fix my set that has the smallest, and I look at what is the second smallest in that. Or you could say, I no longer care about what the smallest is. I just care about what is the second smallest number I could get. And you could ask questions like that. So why do you think I'm bringing this up in this class right now? Yes?
Could be a project.
Yeah. So what tool do you think you might be able to use to investigate this for maybe reasonable values of n? Operations research is a very broad subject, right? Which technique in operations research might be useful? Integer programming. Does this seem like a problem that you could set up with integer programming? Can you put in your constraints to make sure that you never have two things where one divides another? And again, right now I'm not worrying about doing things efficiently. I just want to know, can I set it up so that I can go to the oracle of integer programming and have it run and answer the problem? So how would you check and make sure that I never have two numbers where one divides another? I could look at all pairs here. I could look at 2, 4, 2, 6, 2, 8, 3, 6, 3, 9, 3, 12, and I need to make sure that in each of these pairs I take at most 1. Do we know how to encode you take at most 1?
Yes.
Yeah. We could do things like, x2 plus x4 is less equal to 1. x2 plus x6 less equal to 1. It will be painful to write it down. And we're going to have on the order of 2n squared. It's going to be 2n choose 2, which is going to be roughly, I think, like 2n squared pairs. But it's finite. So for fixed n, we can write these down. How would you find the smallest? Yeah, how would you set this up? So, we want to make sure we only choose n elements. How would you have a constraint that we only choose n elements?
Sum x1, x2.
Yeah, just the sum of the xk equals n. And if we did that, then that would force us to choose exactly n elements. So again, the constraint is not that bad to put in. This is another reason why I like this problem, is it's a way for us to review how we construct constraints. Are there any other constraints we need? This is going to make sure we never have one number dividing another. We choose exactly n numbers. You could, of course, consider, well, what happens if instead of choosing n numbers, we choose n minus 1 numbers? How does that grow the smallest value? Or does it allow us to have a smaller value now, because we have a little bit more freedom? But we need an objective function. Does anybody have any thoughts as to how we can get an objective function? Because we're dead without that objective function. Do you agree that if we do this, we can find feasible solutions? Okay, so this gives us a feasible solution, but it doesn't allow us to solve the problem until we have an objective function. So we need an objective function. What if we just did like minimize x1? Well, we actually know we can't choose x1. So maybe, although if we minimize it, that would be choosing that to be 0. Yes?
I mean, you could minimize the minimum of x1 through xn.
But how are you minimizing them?
I mean, I don't know.
You something with this Sudoku problem where we like assign successive powers to like each xk? And
Yes.
Like that?
So what if we tried to maximize, because if we can maximize, let's maximize, we'll have, 2 to the n, I'm not even going to try to do anything optimal here, times x2. Oh, we'll start with this. And then we'll have n minus 1 to the n minus 1, n minus 1, x. Oh, I guess maybe I should be doing 2n because we go up to 2n numbers. X 3. And go on and on and on like this. We put incredibly high weights. So high that if we're trying to maximize this, having x2 appear is going to beat the hell out of everything else appearing. And then that would force this to try to have x2 chosen. And then the question is just, what are the smallest choices of weights you can use? But this is just proving that in principle, the problem could be done. And you make the weights grow so enormously that this dwarfs this, and this dwarfs the next one. And then if you're trying to maximize it, that the only way you can maximize it is if you ever have a solution where x2 is 1, it's going to go for that. If you have no solution where x2 is 1, it's going to try hard to make x3 be 1. And if you have no solution where x2 and x3 equals 1, it's going to try hard to make x4 equal 1. Question?
Are we maximizing or minimizing?
Maximizing.
Okay.
And then, of course, we don't have a linear program that does maximizing, so you would convert the maximum to a minimum. But to me, it's just easier to view this as a maximization problem. Because the variable is 1 if we choose it, and 0 if we don't. So you'll hear xk equals 1 if choose k, else it's 0. So there's a lot of questions you could ask related to this. You could ask, what happens if instead of choosing n elements from 2n, you choose n minus 1? You could ask, what is the second smallest element? And you might care about the second smallest of all sets, or the second smallest in the set that has the smallest. And maybe try to get some understanding of the distribution there. It may be possible to prove things theoretically. There are some research papers that prove things about Fn, and I think Fn is actually known. And so this would be a theoretical problem that people could do. It has an absolute codable discrete part. The question is, how high of an n could you actually investigate with the computer access that you have? The further you go, the greater, the more information you can see, but the runtime, this looks like it's going to be a nightmare in terms of just the growth of the constraints. Once we're already at n equals 10, that would be actually going up to 20, so it would be like 2 times 2n squared. Oh, it's low. Going to be very large. But this is anyways one theoretical problem. I also talked about the baseball problem if people are interested looking at these statistics. I was talking to some players on the Williams baseball team about data on how often you win as a function of how quickly you knock off the other team's starter. So if people are interested, we have data for a season, and I think it would be fascinating to analyze that data. I am going back and forth with some of my colleagues about trying to get details for other other applied projects, and hope to have more on those soon. All right, this is a good place to stop.